看哪一个？
不过那个好像比较快。
这就减1了，9分减2。你的是9吗？
对，我也是10。Okay, good morning, everyone, and welcome back. My name is Fucheng Wei, and it's my great pleasure to introduce the speaker of this keynote talk, Professor Jieyu Zhang from National Tsinghua University. And Professor Zhang is a world-leading expert in function field arithmetic, with particular emphasis on transcendence theory in positive characteristics. His previous work has made substantial contributions to a study of algebraic relations among periods of P-motifs, special gamma values, and multiple zeta values over function fields, as well as their periodic counterpart. And Professor Zhang has received numerous honors, including the Wu Dayong Memorial Award in 2012, the NSTC Outstanding Research Award in 2012 and 2017, and the Ministry of Education Academic Award in 2023. And today we are very pleased to have him share his expertise with us. And the title of his talk is Multiple Zeta Values and Multiple Items Series in Positive Characteristics. Please welcome Professor Jieyu Zhang.
Thank you, and thank you, Fucheng, for the introduction. And at the beginning, I would like to briefly talk about the classical theory of multiple zeta values, abbreviated as MZVs. So they are generalization of special value of single Riemann zeta functions. So we consider the miscible index. The miscible index is referred to a tuple of positive integers. But for convergence region, we assume the first coordinate is 2. So the MZV is defined by this series. And the weight is defined to be the sum of the components Si, and the depth is defined to be R. So classical MZV is a very popular topic. There are many reasons. So I just list a couple reasons. One reason is that it has arithmetic geometric meaning. Namely, MZV occur as series of mixed motif due to Terrasoma and Goncharov in 2002. And it has connection with modular forms due to Zakier, Gango, Kaneko Zakier, and Kaneko Kasaka, and others. So one central problem in from the point of view of transcendence theory is to determine all the linear or algebraic relations of these MZVs. So for multiple zeta values, it has integral presentation. In fact, it can be written down as iterated integrals, and the form is either the kind of dt over 1 minus t or dt over t. And anyway, so the simplest example is just like zeta 2, 3, and this can be written down in this way, but it just remember that if we put dt over t as the symbol s0 and dt over 1 minus t as s1, then these differentials correspond to this form, s0 raised to s1 minus 1, and s1 blah 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 s0 raised to sr minus 1 s1. So just remember zeta s1 to the sr corresponds to this kind of words. Okay, and from the iterated integral, we can have the so-called shuffle relations. So let's look at the simple example, like zeta 2 times zeta 2. and you just write delta 2 as a iterated integral using this formula, and then we product together, then this becomes, so for individual delta 2 is a iterated integral on a region, and we when we product together, so we integral and over a larger dimensional space. So the integration region becomes delta t uh, product delta u, and with these restrictions, so we just divide this integration region into uh, distinct regions. So, and with the restriction that U1 is larger than T2, U1 larger than T2, so there are 6 possibilities. This just like a shuffle the poker cards. So this is the so-called shuffle relations. So once you integrate over one region, you will produce one multiple database. And finally, you sum together, it comes out that data 2 times data 2 is equal to the sum of the right-hand side. So this is the so-called shuffle relation. And another one, the relation is called the shuffle relation, and some people call the harmonic product or harmonic relations, and it comes from the defining series. And let's look at the simplest case, like a single zeta value. So the product of two single zeta values, by definition, the product of these two sum. And then we partition the pair Mn into 3 possibilities. One is m bigger than n, or m bigger than n, or m equal to n. So the product becomes the sum of these 3 terms. And by definition, this is just the data S1, S2, and this is data S2, S1, and this is S1 plus S2. So this is the so-called this. So I just take the simplest example. Just there you have some feeling how to express the product of two MZV in terms of linear combination of MZV. And if we take S1 to be 2, S2 to be 2, and from this Stafford product, then we get, so this is data 2, 2, data 2, 2, and this is data 4. Okay. Yes. The product of zeta 2 and zeta 2 by this identity is equal to 2 zeta 2 to zeta 4. So this identity is from the defining series. But in the previous page, I mentioned that you can use iterated integral to produce another linear combination called the shuffle relation. So product of zeta 2, 2 is equal to 2 zeta 2, 2 plus 4 zeta 3, 1. So then you have the left-hand side identity from the each shuffle relation. So, and finally we cancel 2 zeta 2, 2. We get zeta 4 equal to 4 zeta 3, 1. So this is the one simple example how we can produce linear relations among MZVs. So this is the spirit of the so-called double shuffle relations. So the idea is that you consider the product of two MZVs, but you express the product into two different linear combinations. One is from the iterated integral called the shuffle product. The other one is from the defining series called the Stafford product. And then you subtract together, you get a non-trivial linear relation. This is the so-called uh, double shuffle relations. And Hoffman puts this into an abstract framework. So we consider the variable S naught and S1, and imagine that S naught is the differential dt over t, S1 is the differential dt over 1 minus t, and we consider the polynomial ring, non-commutative polynomial ring, generated by these two variables, non-commutative, S9 and S1. And we consider this ys to be x naught raised to the S1 minus times S1. So this Ys is correspond to this kind of form. So remember zeta S1 to the SR correspond to this kind of words. And, and here I use Ys to be this. Okay. Anyway, so we can define uh, few subspace H0 and subspace H1 to be of this form. And H is the biggest algebra. And we have the so-called shuffle product notation is star and the sharp is the shuffle product. So we just expand the product of two MCV into two different ways. One is using iterative integrals and put into an abstract form. It's called the shuffle product. And from defining series, we put the abstract formulation. It's called the shuffle product. So namely, if we can define a linear map zeta head, it's called the zeta realization. Once we have all the likely one for the S equal to ys1 to the ysr, you just send it to zeta s1 to the sr. And from the two product, it means that in this abstract space, we have that the product of two MZV can be written simply just like this. And right hand side, we have the data head and this the shuffle of these two words. So I don't need the precise definition. In fact, we can write down the definition of star and the sharp, and in a very simple and concrete way. So the double shuffle relation means that the product of MVB can be expressed as two different linear combinations. So the subtraction gives you a non-trivial linear relation. This is called the double shuffle relations. But in classical theory, people found that this kind of relations are not enough to produce all the relations. So this is the work of Ihara, Kaneko, Zakie in 2006. So in their paper, they had a so-called regularization. So we consider this H1, and as a multiplication law, you use a sharp, and this becomes the algebra generated by S1 over H0. So you just define a map, just send any element to the constant term without. So if you write down as a polynomial in S1 with the multiplication sharp, you send it to constant term. The constant term is H0. And H0, by definition, actually is MCVs are where MCVs are defined. So they found that if you take W in H1, W not in this convergence domain, this divergence. So, but if you surprisingly, if you take a share of W and W naught, but subtract the double of W and the W naught, and then take the regularization, then take the data, this becomes 0. They found that this gives give some relations inside this MZV. Namely, this is inside the kernel of data head. And this is the famous conjecture of Ihara, Kaneko, Zakie. They conjecture that the idea, so the all the relations are coming from the regularized double shuffle relation. Namely, kernel of data head is generated by this element. So this is the Ihara, Kaneko, Zakie conjecture. And for the classical theory, I use one more minute to mention about the central conjectures in the classical theories. One is the so-called Goncharov direct sum conjecture. If you put data n to be the Q vector space spanned by NZVs n, and Z is the NZV EQ vector space spanned by 1 and all MGVs. And there is some conjecture says that Z can be written as a Tarism. In this way, MD is a graded algebra, so graded by weight. So namely different weight MGVs, they must be linearly independent. Okay? And the other one is the famous conjecture due to Zakiye. So this is the so-called Zakiye dimension conjecture. So you define a sequence Dn, and simply Dn is defined from this Laurentine series. And Zakiye conjecture that the dimension of multiple data values of weight n should be equal to this Dn. And Hoffman, so this is Zakiy's dimension conjecture. But Hoffman gave a more further conjecture. He gave a conjecture regarding how to find the basis. And he conjectured that it's simple. You can, when you fix the weight n, you consider all turbo with some Si equal to n. And each digit, each component Si is either 2 or 3. Then there must be a basis. Okay. And the following are two known results in the classical theory. So these two are big papers. One is in Dimension, the other one is in Annals. So Terosoma and Gongcharo showed that Dn is the upper bound for this dimension. And Brown showed that Hoffman basis conjecture is the Laurentine set. So actually, Brown's theorem implies this upper bound result. So this is the classical theory as my motivation. So now I'm going to move to the function field side. So I use FQ to be the finite field of Q element in Keras P. And A is the polynomial ring in the variable theta over FQ. And K is the field fractions. And K infinity is the completion of K at the infinity place. And C infinity is the infinity periodic completion of algebraic closure of K infinity. And K bar is the algebraic closure of K inside C infinity. And A plus is the set of all monic polynomials in A. So just this is the picture for analog. So A plus is the analogous law of the set of positive integers, and A is the row of the integers, and K is the row of rational numbers. K infinity is the row of real numbers, and C infinity is the row of the complex numbers. And K bar is the analogous law of arbitrary numbers. So function field multiple zeta values are defined by Takuro, and they are generalization of Kalis in that case. That's one case. So the definition is simple. So you consider the any tuple of positive integers, then you consider this series. So A plus is the analog set of positive integers. So you consider all AI, but with the restriction that the imperative S value of A1 is bigger than imperative S value of A2. And we can define the weight and the depth, such as the classical case. So this is in the non-committing space, and Takuro showed that his imperative MGV are non-vanishing, and this imperative MGV have arithmetic geometric meaning in the sense that they are periods of certainty motives in the function field case to Anderson and Takuro. And in the case, and so it was due to Professor Jing Yu, and I generalized it to arbitrary depth. So in function field case, all multiple data values are transcendental over time. And in the classical case, the transcendence of MGV are still an open problem. And the topic is to determine relations. Okay, so here we have analog of direct sum results. So I use this Mescal N to be the K vector space spanned by with N and GV. And if I put a bar, means that they are vector space over K bar. Okay, so similarly, we can define Mescal Z and the Mescal Z bar generated by spanned by 1 and all MZVs. And Takuo showed that the product of two MZVs can be written down as an FP combination of the same weight. So the product of these two is contained inside here. So this Z forms an FP algebra. And 1 decade ago, I showed that it's a gradient algebra. So this Z can be decomposed into this direct sum. And furthermore, I showed that K-linear independence of MZVs would imply K-bar linear independence. So this is the analog of the classical Baker's phenomena, linear independence of logarithm of great numbers. So this direct sum result is the first step towards determining all the algebraic relations among MZVs over K. So here we have analogs of the classical Zackius dimension conjecture and Hofmann basis conjecture. So the analog of Zackius dimension conjecture was equal to 12. So simply we define a sequence of positive integers from this Jonathan series. I use dn prime, and he part of conjecture says that the dimension of the MZV of with n over k is equal to dn prime or n. And furthermore, Takuo gave an analog of Hofmann's basis conjecture. So for this vector space, he considered all turbos of weight n, and if we require the last coordinate to be less than q, then and previous r minus 1 coordinate to be less than or equal to q, then Takuo conjectured that this zeta a evaluated this kind of turbos, then there should be a basis. So certainly, if Takuo's conjecture is correct, then Earth's dimension conjecture would be true. So so the following theorem is my joint work with my former student Chen Yanzhong and Japanese collaborator Yoshinori Ishiba. And we show that Takuo's basis conjecture is true. And actually, this result was proved almost at the same time by two groups. And the other group is Im, Kim, Lei, Egotak, and Fong. And two papers were published in the same journal, but in different years. So anyway, so we have the results of the analogs of Zackius dimension conjecture and the Hofmann basis conjecture. So how to describe the relations? So actually, Takuo showed that the product of two MZV can be written down as an linear combination of MZVs of the same weight, but his proof is just the existence. But Huizhen Chen gave a concrete example for the product of two single zeta values. So, and later on, Yamamoto used Huizhen Chen's formula to define an abstract product multiplication law, the so-called Q-sharp product. I use the bullet. So now we can consider this H naught to be, so we consider all the indices, and we consider the vector space spanned by indices. So for the empty set, we use H naught, and I forgot over FP to emphasize the vector space is over FP. So H over FP is the direct sum of all Hn over FP. So Hn is the FP vector space spanned by this the simple index with weight s equal to n. Anyway, Yamamoto gave a and very concrete. And Shi Suhui, she was Chinese. She was a former student. Cool. So here, we can consider the data realization. So in space, map to space of MGBs. So here I use H over K using the same definition, but just replace the field FP by our best field K. So Shi verifies Yamamoto's Q-shuffle product exactly identical to Parkour. So namely, the product of these two index on this abstract space, you take the data realization, and this is equal to the product uh, two MDVs. And for this space, H over FP. So by definition, you can check that it's commutative. But still, in her PhD thesis, he conjectured that this should be an associated algebra, this H. And the associativity, so it is a very simple definition in abstract algebra course. But in this setting, it's a typical problem. Yeah, I'm very glad to announce that, yeah, this is a current result by 4 students, Tsinghua, due to Zhang Tingwei, Chen Songyun, Huang Feijun, and Cui Hongqiu. So they show that this associated algebra. And so if we replace the best field FP by K, then it's also associated. So because this map is surjective, right? And both are commutative associated algebra, and we have the algebra homomorphism. So by first isomorphism theorem, I'm very ashamed. You quotient the kernel, then we have this isomorphism, right? So how to characterize this kernel? And this now this is the result due to the associativity. So we use a result from my paper with Chen Yanzhong and together with the direct sum results, we can create a very concrete but very, very complicated linear relation from this abstract space. And the kernel can be simply characterized by this, the subtraction of S and the U evaluate S, or S in Parkour index. So remember, in the classical case, Ihara Kaneko's conjecture, they predict how to characterize this kernel data head. This comes from the regularized double shuffle relation. But in the function field side, we did not have the double shuffle. So the best we can do is to characterize the kernel in this way. But to characterize the kernel, we have to say that this is an algebra, associated algebra. And so thanks to the 4 students. So basically, so we fully understand this kernel, the generators of this kernel. So namely transcendence theory of MZVs over the best field, function field K, now is fully understood. So we can ask a question. So what is the how about the transcendence theory of MZVs over FP? So FP is our prime field, but in the so as I mentioned here, so K is the FQ theta is the analog of the rational numbers, but Q is the prime field of C, right? But OK is FQ theta. So the smallest field is FP. So there is no such question in the classical case. But the transcendence theory of MZVs over FP is still missing. And this is the current project I'm thinking about. So I simulate an isomorphism conjecture. So recall that Z over FP is the FP vector space spanned by 1 and over MTVs, and by the result of 4 statements. So this H over FP is a commutative and associative algebra, and we can map this index to the zeta A evaluate S. But now both sides are over FP. And again, this is an FP algebra homomorphism. So here is a model conjecture. So this should be injective. So namely, data duration over FP is an isomorphism. So I will explain why. Anyway, this is just a conjecture. I'm not sure if it is correct, but I guess this should be correct. And so I would like to mention this isomorphism conjecture would imply two conjectures of Parcours. So remind you, the isomorphism conjecture is very simple. So the generalization gives you the isomorphism. And Parcours has two conjectures. One is the so-called linear conjecture. Linear independence. He gave a conjecture that all MCVs are linearly independent over FP. And okay, so assuming this isomorphism conjecture, I now we explain why Parcours linearly independence conjecture will be true. So by definition, so all indexes are linearly independent inside this space, and because these are isomorphism, and this index is mapped to ZIAS. So left hand side are linearly independent, and of course right hand side are linearly independent. So isomorphism conjecture would imply Parcours linear independent conjecture. And Parcours has another linear conjecture, the so-called, I call it uniqueness conjecture. So he conjectured that there is only one product on MCVs. So in terms of the abstract space, in other words, there is only one product on this H over FP. So if we have another, so I explain, because isomorphism conjecture implies linearly independent conjecture. So now I explain Parcours linearly independent conjecture implies uniqueness conjecture. If this is okay, then this isomorphism conjecture would imply this conjecture. Okay, so suppose we have another product, I use star, and which is not equal to the bullet, the Q shuffle product. Namely, for some S and S prime, the product of these two index is different from this the product of these two index. But once you take the zeta hat realization, they are equal to this product, zeta AS and zeta AS prime, right? But these two products are different. Namely, you subtract S star S prime and the S bullet S prime. They are linear combination of some other indexes. So you subtract this, then they are this is equal to 0. But this subtraction are, are, are given in a linear combination of MCV over FP. So this give a non-trivial FP linearly dependence of some MCVs. So this would give you a contradiction to Parcours linearly independent conjecture. So let me, as a conclusion, if this is correct, the Morgan conjecture is correct, then these two uh, conjecture of Parcours would be correct. So finally, oh, okay. Yeah. So finally, I would like to mention about a multiple Einstein series. So the multiple Einstein series, or in the classical case, was due to Gango Kaneko Zakie for the depth 2 case, and later on generalized by Bachmann to after that. So, so H is the this BBH is the upper half plane of the complex numbers. So for any tau, we consider this lattice E tau plus C, and they first gave an order on lattice, just like a less topic order. So first, for any omega in this lattice, a tau plus b. So a, b are integers. So we say a bigger than 0 means that either a bigger than 0 or if a is 0, then we require b is positive. And the 2 points in the lattice have the this order m bigger than n means that this subtraction is bigger than 0. So then we consider this kind of inequality in the via this order. And the double Einstein series is defined by this form. We just sum over all elements in this lattice, this inequality. So this is the classical multiple Einstein series. And remember, we have the analog of A plus. So this is the analog of N, A is the analog of Z, and C infinity is the analog of C. So now we have the twin field upper half space. This C infinity subtract the K infinity denoted by omega. This plays the analog of compressed upper half plane. So we can consider a similar situation for the lattice of rank 2 inside C infinity. So it was due to Huizhen Chen. So she modified the idea of Kanko Kaneko-Zakie to define a partial order on elements of lattice. So you just think of the role of A plus as analog of past integer, then you know how to define this. Due to the limited time, I just let you know that we can define this kind of analogous double Einstein series. And just last year, so I suggest for students to generalize this to higher depths. So actually, there are rich analytic functions on this twin field upper half space. So this is the work of, and the for students' work is that actually once you know how to define depth 2, then you can generalize to higher depth. But here omega r is the twin field metric space. So in terms of component, we require the last coordinate is to be 1, and all coordinates are linearly independent over K infinity. Anyway, I avoid this precise definition. And what I want to say is that for any couple of positive integers, we can define this after that multiple Einstein series in terms of this form. And in the last 2 minutes, so let me summarize what the students work. So Zhang Chen and Huang Cui. So I'm not this Zhang, so it's Qing Zhang. So multiple Einstein series of R are rigid analytic functions on this twin field metric space. And they compute the so-called T expansion of the multiple Einstein series. And the constant term is just multiple zeta value. And they show that Takuma shuffle product is lifted to relation among functions of the multiple Einstein series. And the one crucial tool is that they use multiple Einstein series, and so a rank R denoted by this MES bracket R is they show that this function FP algebra, and they form a projected system when R varies. So you can consider this inverse limit, and this forms a ring. And their great idea is how to show the difficult problem of the associative. They show that this abstract space R, you have an injective FP algebra homomorphism. And because the FP algebra homomorphism, right hand side is associative, so left hand side is also associative. And so, and therefore they verify this conjecture. So my current project and goal is I hope to use their tools, the tools they develop using multiple Einstein series. I hope multiple Einstein series can be used to prove the Asimov conjecture that I propose. So I think I stop here. Thank you for your attention.
Are there any questions? Yeah, I have one question in about your isomorphism conjecture.
Yeah.
Is it possible to compute using computer to compare the dimension of each Hn and Zn computationally?
Because Takuo conjecture that they have to be linearly independent over FP.
Yeah.
So basically, I guess
The
he
dimension is-
already all are linearly independent over
Oh,
FP.
I see. Okay.
So non-trivial linear relation only occur over K.
Oh, I see.
So
I
what
see.
I say is that transcendent theory of MZV over K is fully understood, but missing part is over FP.
Oh, I see.
And Takuo's conjecture is that all are linearly independent.
Oh.
And from this part, I guess he and his student may already had done a lot of computation, and that's why he put it. He had this conjecture.
Any other question? If not, let's thank Professor Zhang.
Thank you.